Okay, great. So everybody sees this okay, right? Okay, so if it's too small or the handwriting's not legible enough, please let me know. Okay, so right, so I'm going to talk about something called D invariance of a certain type of three manifold obtained by taking covers. Okay, so right, so these computations will support a conjecture, which I'll talk about at the very end, and this is work in progress with Marco Marangan. Okay, so for us today, Y will denote a three manifold, closed, no boundary, oriented, and we fix a smooth structure and a metric. And then all other three manifolds will be equipped with spin structures. Okay. So let me talk a little bit about what a spin structure is. So a spin structure is a lift of the frame bundle. Okay. So a spin structure in Y is a lift of the frame bundle over Y to a spin 3 or SU2 bundle over Y. Okay. Right. So I'm not really going to say much more than that, but it's a certain type of lift. Okay. So some important properties for us is that every oriented three manifold will have a spin structure. And if we fix one of them, then we can index them by H upper 1 with Z2 coefficients of the three manifold. And then another thing that'll be important for us is the notion of a spin C structure. So every spin structure gives rise to a canonically defined spin C structure. So let me tell you what that is right now. Okay. So a spin C structure is it's a lift as well of the frame bundle again to a different structure group. So we're looking at spin C3 now, which you can think of as U2. And again, it's a bundle over Y. Okay. So for us, the properties we care about are one, they also exist on every three manifold, and this is because spin structures exist, and again, we can think of them as cohomology classes if we fix a base spin C structure. So they're indexed by H over 2 with Z coefficients. Okay, so right, so I didn't say anything about how to go from spin to spin C, but okay, but maybe you can sort of believe that once you have one type of lift, you can get another one. Okay, so for the rest of the talk, we won't care about any three manifold. Why? We'll only care about those that have the same homology with Q coefficients as S3. So these are called rational homology three spheres, QHS3. And in 2004, Oshrath and Szabo showed that to three manifold to a rational homology sphere equipped with a spin C structure, one can associate a rational number called the D invariant, and it's, let me give you like a very fast sketch of the definition. So how do you do it? Well, to this pair, you get a bunch of groups or really Z2 of U modules. There's the HF infinity version, the HF minus version, the HF plus version. There are other versions, but for us, these are the ones that are important, and at least for now. And these three modules, they fit inside a long exact sequence. I'm not really going to talk about, I mean, they come from the, basically, most of the maps are determined by the definition of these various groups, and then there's a connecting boundary map. But anyway, what's important is that we have a map, a projection map pi from HF infinity down to HF plus. I didn't define what these modules are, but that's actually not going to be so important for us, but they are. But anyway, we have a map from HF infinity down to HF plus. We call it pi, and the image of pi, well, it's a tower. So it ends up being, if you think of the image of pi as a z, as a module over Z2 adjoined U, then it's Z2 of U inverse modulo Z2 of U. So in other words, it's just the negative U powers starting at -1, okay, and going down. So we denote that by tau plus, we call it the tower of HF plus because it lives inside HF plus. And we define the D invariant to be, so there's a rational grading on all of these groups, and it's going to be the rational grading of the element in this tower that corresponds to the element U to the -1. Okay, so that's the D invariant. Why do we like it? Well, Osheth and Szabo also showed that when you start off with, so there are lots of reasons, but I'll just name a couple of them. These are the classical ones. So they also showed that when you start off with something that's not only a rational homology 3-sphere, but also an integer homology 3-sphere, so it has the same homology as S3 with Z coefficients, then this D invariant sort of interpolates between the Euler characteristic of a quotient of HF plus and something, and the Casson invariant, okay? In other words, one is equal to, the Euler characteristic is equal to the Casson invariant plus this D invariant number. So it turns out that when Y is an integer homology 3-sphere, the D invariant is an integer. In fact, it's an even integer. So if you add this, you do 1/2 this even integer plus lambda, you get the chi. Okay, so, and then another reason is that it helps us determine when lens spaces come from positive integer surgeries on knots. So this is all pretty classical. Okay, so that's the D invariant in a nutshell. So for the rest of the talk, I want to focus on double branch covers of links in S3. Okay, so these are obtained by taking normal covers of the complements of these links. Well, there's you take a Cypher surface as well, and then you fill in the boundary components with solid tori so that you map all the meridians to 1. Okay, so right, so the case that I want to look at first is where there's only one component, so the link is a knot, and it turns out that the double branch cover is a rational homology 3-sphere. Okay, so this is pretty classical, right? So it's because when you start off with a knot, the determinant is it's non-zero. It's always a positive number, but it's non-zero here, and in fact, it's always odd. And then right, so H1 is determined by this determinant, and H1 is all you need to get the all of the homology groups essentially for a 3-manifold. Okay, so and then the other fact is that there's only one spin structure. Okay, so now we're going back to spin structures, and again, right. So this is also pretty classical. Okay, so now so to this unique spin structure, let's consider the associated spin C structure. We're going to call that S0, and an observation made by in 2005 by Manolescu and Owen says that the D invariant of this 3-manifold, this double branch cover of our knot at this unique spin C structure, that's congruent to -1/4 times the signature of the knot. Okay, so mod 2z. So you're just adding and subtracting multiples of 2. Okay, so why is this true? Well, there's a formula for the D invariant, and there are more terms in this formula than in the signature in the -1/4, but it turns out that when your 3-manifold is bounded by a 4-manifold and its spin, a lot of these terms go to 0, and what you're left with is just being congruent to -1/4 times the signature. Okay. So Manolescu and Owens, they also showed that if the knot is alternating, has this additional property of having an alternating diagram, then the D invariant of this 3-manifold up above at this unique spin C structure is on the nose -1/4 times signature. Okay. And in fact, if you use recent results of Jin-Fen Lin, Danny Ruberman, and Nikolai Savelyev, you can push this to the following observation. If your double branch cover is an L space, then the D invariant is again -1/4 times the signature. So this is a generalization because double branch covers of alternating knots are known to be examples of L spaces. Okay, so what's an L space? Well, it's a rational homology 3-sphere with simple Hager-Floer homology. So what you get when you look at you can look at different flavors, but I guess I wrote it for the hat version here. For every spin C structure, that abelian group is Z2. Okay, so one thing you can ask is what happens when you pass to more components, when what you're branching over is not K, but L. Okay. So there are a couple of important differences when L is a multi-component link. First of all, the double branch cover may not be a rational homology 3-sphere. So for example, when you start off with the 2-component unlink, the double branch cover ends up being S2 cross S1. So I don't know if you guys have, if you think much about double branch covers, but this is because you can break up S3 into 2 3-balls, and each 3-ball has got like a pair of disjoint arcs, and so you branching over all of S3 along the L is the same thing as branching along each of the 2 3-balls, where the branch that is that pair, and then you get these 2 solid tori and you glue them together in the right way, and you get S2 cross S1. Okay, so what do we do? Well, we're just going to consider, we're only going to consider the links over which the double branch cover is a rational homology 3-sphere. Okay, and then and the other problem is what happens when the double branch cover. So the other problem is that the double branch cover no longer has a unique spin structure. So it's a fact that spin structures on double branch covers are classified by quasi-orientations on the link. So a quasi-orientation. So what is a quasi-orientation? It's a pair of orientations on the link. So you take an orientation and then you reverse your choice on all the components. So it's just orientation and then it's negative. And if the link has got m components, then there are 2 to the m minus 1 quasi-orientations. So in particular, if m is equal to 1, but there's only 1 component, then you have 1 quasi-orientation, the orientation that you picked, and then the opposite orientation. Okay, so right, so that means that there's, and we've already seen that there's only 1 spin structure when you're branching over or not. So okay, so anyway, so here, what do we do? Well, we're just going to consider all the spin structures on the double branch cover. Okay. All right, so in 2018, Lin, Ruberman, and Savelyev showed that when the double branch cover of your link is an L space, summing up all the D invariants over all the spin structures, that's the same as summing up all the signatures over all the quasi-orientations. So sorry, I didn't say what QO is, but QO is this thing right over here. QO, that's the set of quasi-orientations. I should have just called this. Okay. Right. So you sum up all the signatures for all the quasi-orientations, and you multiply that by -1/4. So here, when you're in the links case, the signature will depend on the orientation you've picked, but only up to its complete reversal. So given a quasi-orientation W, it makes sense to talk about the signature of the link with that quasi-orientation. So you're going to sum up all these things, multiply by -1/4, and that gives you the sum of all the D invariants. So a natural thing to ask is, well, a natural thing to conjecture is when your double branch coverage is an L space, each of the pieces in the sum, they're equal to each other. When you pair up, when you look at the D invariant at a spin structure, well, at the spin C structure associated to a spin structure, and then take the signature of the corresponding quasi orientation. Okay, and so here's some supporting evidence. So in 2013, Liska and Owens, they showed that if you start off with a quasi-alternating link, then the D invariant is equal to then we have this property, namely for every pair of spin structure together with the associated quasi-orientation, the D invariant is equal to -1/4. And it's known that when the link is quasi-alternating, then its double branch coverage is an L space. So this is sort of, okay, so this is evidence that this conjecture could be true when the link is quasi-alternating. So what I want to do for the next maybe 10 minutes or so is to talk about this theorem that shows that there are examples of non-quasi-alternating links, infinite families of them, whose double branch covers are L spaces, and then for every pair we get this D invariant property. Okay, so all of these examples are they come from the Montesinos family. They're three-legged, so so the associated graph has got 3 branches, yeah. So so here I've just written down a standard way of describing one of these three-legged Montesinos links. So this is what they look like, what one of them looks like. Okay, so if you take so if you take T1 to be 10/3, T2 to be 4, T3 to be 10/7, you take your E to be 1, then so there's a way of drawing this from these numbers, and basically you're going to take a continued fraction just decomposition for each one of these TIs, and that tells you how many twists to use. And so we see 3 branches because there are 3 TIs here. Okay. Okay. So here's a sketch of the proof. Okay. So how do we know they're not quasi-alternating? Well, in 2017, Adma Issa classified, determined when Montesinos links, not just 3-legged ones, but just in general, he determined when Montesinos links are quasi-alternating, or equivalently when they're not quasi-alternating. So it turns out that in the 3-legged case, a Montesinos link is not quasi-alternating if and only if we're in one of these 2 situations where E is 1, and then we get this property, or E is 2, and we get an analogous property. Okay, so our families lie in these 2 cases, so they're not going to be quasi-alternating. Okay. And then how do you know that they're double branch covers or L spaces? Well, there's another classification for Montesinos links, branching over Montesinos link. Well, branching over like a 3-legged Montesinos link, and so this classification is kind of ugly, so I didn't put it down, but it's due to Eisenbud, Hirsch, and Neumann, a combination of papers, Jenkins and Neumann, and then I think, and then Ime. Okay, so our families also satisfy this, and then I guess the most interesting property is the property that motivates the whole project is that we get this relationship between the D invariant and the signature within each spin quasi-orientation pair. So how do you see this? Well, each one of these double branch covers, because because L is a Montesinos link, the double branch cover is going to end up being the boundary of a plumbing 4-manifold associated to some tree, a weighted tree. So this is like a graph that's got no cycles, and there's a number and integers on each vertex, you know, the edges and the integers, they tell you, you know, they tell you which D2 bundles over S2 to Plum. There's a Pullman construction, and then you take the boundary of this four manifold that you get, which we're calling X of the tree, and that's the double branch cover. Okay, so so this is how Cepheid-Fibert spaces are constructed. Okay, so in our examples for our L's, this four manifold is negative definite, and then they're also the resolution of a rational complex surface singularity. Right, so there's a result to the Nemeth that tells you how to determine whether a four manifold is you know, a rational complex surface, you know, the resolution of a rational complex surface singularity, and it says that basically when your four manifold comes from a weighted tree, it's one of these things when the boundary is in L space. It's exactly one of these things when the boundary is in L space. Okay, so right, so and then we use some classical results. So this is yeah. So this result isn't like super new; it's sort of new-ish, and so we use a combination of classical results to get this. So by results of Stieptjes and Nemeth, we know that because our four manifold, because the double branch cover is the boundary of a negative definite four manifold, that's also the resolution of this particular type of singularity, then we get the D invariance equal to -1/4 times something called the Neumann mean bar invariant, and then we use some other. There's another result by Savilio that says that -1 times Neumann's mean bar is always the same thing as the signature of the link we're branching over. Okay, so yeah, and then I just so that's the proof, and then so I thought I would include some comments about mu bar for those of you who haven't seen this before. So mu bar is a lift of Rockland's Neumann's mu bar invariant is a lift of Rockland's. Sorry, I meant to write mu invariant, not mu bar here. And so Rockland's mu invariant is for spin three manifolds, and it lives inside Z16. You can get like an integer invariant from integer homology spheres, but here we want to, I guess we want to just work with spin manifolds, and then mu bar is actually only defined. Maybe I should have said this first. It's only defined for Cepheid-Fibert spaces equipped to spin structures. So these exactly the boundaries of these Plum four manifolds. Okay, so that's pretty much it. That's all I wanted to say.
Let's thank BT